Let us start discussion on DPP of Simplex. Which of the following is true in case of Simplex method? The constants of constraints equation may be positive or negative. It is wrong. You know what the option is telling? Suppose the constant is 2x1 plus x2 plus x3 less than equal to minus 3. So right hand side, the statement is telling right hand side can be positive or negative, which is wrong. To begin Simplex, this must be positive. If it is negative, then the entire equation is multiplied by negative. So minus 2x1 minus x2 minus x3, this sign will change. Right hand side must be positive, otherwise we cannot begin the Simplex iterations. Okay. Inequalities are not converted into equations. No, that is also wrong. By adding slack or surplus variables, inequalities are converted into equations. Second statement is also wrong. It cannot be used for two variable problems. 2, 3, 4, it can be used. Then the Simplex algorithm is an iterative procedure, because first, second, third, till we get the optimum. Okay. What is the shadow price? Suppose this is the feasible region. Constraint 1, constraint 2. I'm just taking an example just to make you understand, to explain what is the shadow price. Let us say first constraint is 2x1 plus 3x2 less than equal to 19, and the second is x1 plus 5x1 plus x2 is less than equal to 30. And let us say, I'm just taking an example, let us say the optimum point is 2 and 5. So if I apply here 4 plus 15 is equals to 19. So left hand side is equals to right hand side. These constraints are resources. These constraints are resources. So this resource is fully utilized. This resource is fully utilized. And let us say if we apply here 10 plus 5 is 15. So left hand side is less than right hand side. So this constraint is not fully utilized. This constraint is not fully utilized. So this is my objective function. Suppose I want to increase the objective function. I want to increase the value of objective function. Or you can say I want to increase the output of my plant. This constraint will not allow. Because its resources are fully utilized, this constraint will not allow. So you know what is the shadow price? To increase the output per unit, how much money needs to be spent on this facility. Maximum price which should be paid to obtain an additional unit of resources. For getting additional unit of this resource, how much price we have to pay so that I can increase my output? This is called a shadow price. So wherever the resources are fully utilized, how much money needs to be spent on those resources to increase one additional unit is called shadow price. But what question is saying? Resource is not fully utilized means like this. If the resource is not fully utilized, the shadow price is 0, because by increasing the capacity of this resource, there is a capacity. Even 5 more units, 15 more units can be utilized at the existing facility. So shadow price for this resource will be 0, because nothing to increase the output or increase this resource, nothing needs to be spent on this resource. But to increase the output, something we have to spend on this resource. I will give you one example just to give you some idea. Suppose this resource is a welding transformer. Let us say duty cycle is 30%. Duty cycle means out of 10 minutes, 3 minutes continuously I can operate this transformer. Now I have more load on the welding transformer, so this has to be increased to 50% duty cycle. In 10 minutes I want to operate for 5 minutes. So certainly the coiling, all these things needs to be changed to increase the duty cycle of the transformer. So how much money we have to pay? Let us say 10,000. To increase the capacity of welding transformer, 10,000 piece needs to be paid. This is called shadow price. So for resource not fully utilized, shadow price is 0. The variables which have not been assigned 0 are called basic variables. First of all, non-basic variables we are assigning 0 values. Simplex method of solving linear programming problem uses only the corner points of the feasible region. See, this I have explained in the class. Suppose this is the feasible region. So I am starting from origin. In my first table, Simplex is having 2 routes, either go by this path or go by this path. Either go by this path or this path. So which decision I will take? By taking decision on any variable so that my profit increases. Maximum negative from Ej minus E0. So let us say I am taking decision on X variable. So I am moving here. I reach this corner. Now going from this side till we achieve the optimum point. Because to achieve this optimum point, there are 2 routes, here, here, or here, here. How I will go? Wherever I am getting the maximum profit. So I will go from corner to corner point in Simplex iterations. This I have explained in the class. A linear programming problem with mixed constraint means it is having this also, it is having this also. I will use bigger method. You know how? Here I will use slack variable, and here I will be use surplus variable and one artificial variable and one artificial variable, and this method is called big M method. Okay, na? Why it's big M? Because value of M is almost infinite. Okay. Now here, the right hand side, it is nothing but B divided by entering column. There are some values and we select minimum positive, including 0, correct na? But if all the values are negative, it is unbounded solution. It is unbounded solution. If the optimum of a linear programming problem is dual value corresponding to the particular, see, there is something called complementary slackness theorem. Complementary slackness theorem. What this complementary slackness theorem says, for any primal constraint, if left hand side is equals to right hand side, like for any constraint, if the left hand side is equals to right hand side, it means slack variable 0. It means slack variable 0. So complementary slackness theorem says the corresponding dual variable y1 will have some value. Will have some value, 100% it will have some value. One beautiful problem appeared in GATE based on the complementary slackness theorem. Okay, now, for a primal, if left hand side is less than right hand side, it means slack variable will have some value, 2, 3, 5, because let us say this is 14, this is 30. So slack variable will have 16 value. In a primal, if the slack is having any value, it means it's corresponding to dual variable will have 0 value. It's a complementary slackness theorem. So if the optimum of a linear programming problem, if the dual variable corresponding to a particular primal constant is 0, it means it is this case. So it means slack of the primal is having some value. Slack of the primal will have some value. ठीक है ना? So changing the right hand side of the primal constant will disturb the optimum solution. That is correct. Okay na? See this one? Now, a linear programming problem with 3 variables and 2 constants can be solved by graphical method. No, it's wrong. So remove from options wherever 1 appears. Only left out is D. For solutions of a linear programming problem with mixed constant, big M methods can be employed. Correct? Mixed constant means some are less than equality, some are more than equality. So big M method has to be used. Okay. In the solution process of a linear programming problem using big M method, when the artificial variable leaves the basis, it never reappears again. We can delete that column itself. So answer is D. Let us plot it. O 0 2 2 0 and then 4 by 3 4 by 3. This is the feasible region. Okay, this is the feasible region. and the maximizer is x1 plus x2. The corner points of the feasible region are this one. So we have to find out if an additional constant x1 plus x2 less than 5 is added, the optimum solution is. This is the question. If additional constant x1 plus x2 is less than 5 is added, what is the optimum solution? So it's a x1 by 5 plus x2 by 5 less than equal to 1. So 5 here and 5 here. So you can just plot it that one. Okay. So these are the constraints I have. Two x1 plus x2. Let us say this is x1. This is x2. It is a 2x1 plus x2 less than equal to 4, correct, no? And this will be x1 plus 2x2 less than equal to 4. So I am making the constraint like this. Okay. So now if you x1 plus x2 at 5 is added, na, it will be like this. You can try constructing it. So this will be the redundant constraint. So you can plot it. So still even after adding, because this constraint is redundant, my solution will still be 4 by 3, 4 by 3. Solution is still be 4 by 3, 4 by 3. Okay, na? But the second part of the problem is, let y1 and y2 be the decision variables of the dual, and v1, v2 be the slack variables of the dual of the given linear programming problem. The optimum dual variables are. So x1 is equals to 4 by 3 and y1 is equals to 4 by 3. Let us apply the complementary slackness theorem. So what is my constraint? 2x1 plus x2. 2x1 plus x2 less than equal to 4 and x1 plus 2x2 less than equal to 4. Okay, na? And my optimum point is 4 by 3, 4 by 3. So let us apply here. Let us see if the left hand side, right hand side is okay. So 2 into 4 by 3 plus 4 by 3, 3 10 14, 3 6, no, 8 by 3 plus 4 by 3, 12, 4. So left hand side is equals to right hand side. So here slack is 0. Slack is 0. Now for here 4 by 3 plus 2 into 4 by 3 is also 4. So here also left hand side is equals to right hand side. So here slack is also 0. So what we discussed, complementary slackness theorem, that if the slack is 0, then dual will have some value. Dual will have some value. So decision variables will be y1 and y2. Decision variables will be y1, y2. Suppose, I'm just giving the example, suppose first constraint, left hand side is less than right hand side, and the second constraint, left hand side is equals to right hand side. So now in this case, here there is some slack value. It means y1 will be 0 and y2 will have some value. Okay, na? So now the optimum dual variables will be v1 and y2. v1 and y2 in that case. So complementary slackness theorem is a very important theorem. So that was your DPP.